So what we're getting into, and this is going to be a topic for quite a bit in the future. A good portion of Calc 2 is dedicated to a subject here. This subject is substitution. And what this is going to let us do, it's going to let us do some integrals that are kind of tricky, that aren't going to be all that easy. Integrals we don't have direct formulas for. Now let's suppose we have a function, capital F of x. And if we take the derivative of it, we get little f of x. Or put another way, if we integrate little f of x dx, we get capital F of x. So capital F of x is an antiderivative of little f of x. So what we're going to consider is this. Let's say we have something like this. We're going to take a composition of little f of x with little g of x and multiply this by g prime of x. And suppose we don't have, or we don't know, let's look at my pins again. So we don't know an anti-derivative for this. So in other words, if we integrate this peculiar function, we don't know what we're going to get. Which, to be fair, I mean, this is a lot more complicated than integrating just plain f of x. But we're going to come up with a trick. And this is how the trick works. So number one, let u equal g of x. Then if we take the derivative du dx, we get g prime of x. Or if we multiply both sides by dx, we have du is g prime of x dx. So here's going to be the neat thing. In our integral, we'll replace g of x with u and g prime of x dx with du. So what this should do is just make life much simpler. So that becomes u. This is du. So we get f of u du. And so what this will give us, now we know the antiderivative of f. We've seen that. That was that capital F. So we get, ooh, switch my pen. So you get capital F of u, because that's what the integral of this is. But we know what u is. U is g of x. So this will be f, capital F, of little g of x. And that's the method of substitution. And it's one of these things where you kind of practice it after a while, and you'll get the hang of it. There's some neat tricks to it. It's kind of a creative kind of mathematics. You can have a lot of fun with it. It can be a little tricky at times. I will go over some good ones today. So not always do you have to use it. Sometimes it can save you from having to do a really grueling integral. So let's say we're going to do this. So the way we would do this before is we would expand this. And let me tell you, you're going to be here a little while expanding that. That's going to be kind of a really tough expansion. So what you can do instead is we'll do a u substitution. Let u be 2x plus 4. And then now we calculate du dx. So we know we're going to replace this with u. We have du dx, and that's going to be just 2. Derivative of this is just going to be 2. And multiplying both sides by dx, we get du is 2 dx. So here are the key substitutions. This and this. So there's our u and there's our du. Now, if you take a look at our integral, we can rewrite this as 2x plus 4, 12, times 2 dx. So this will now become du, and this inner part is going to be u. And so now the integral becomes something more manageable. U to the 12 du. And if we think about antiderivatives, this is going to be u to the 13 over 13 plus c. It's going to be plus c. Again, we don't have any bounds on here. This is an indefinite integral. So we're going to get that plus c. And then now, remembering what u was, put this back. We'll get 2x plus 4 to the 13 over 13 plus c. And the moral of the story is that instead of expanding this with an exponent of 12, this whole thing, this is just a whole lot easier. So any questions about that? All right. So let's say we have something like this. Now suppose we need to integrate this. So one thing we can do, and they tend to do this, I think, in the text, they'll give you some hints on what, which one of these we should use. And one thing you could use, let me take a look at this. They use a peculiar integral on this one. Oh no, we could do this. So we can let u equal 1 plus square root of x. And if we take the derivative with respect to x, we'll get 1 over 2 square root x. Or du equals dx over 2 square root x. Now there's a problem here. We can get a square root x under dx. We've got that. But we don't have a 2. So sometimes what you'll see people do, and this works for constants, multiply both sides by 2. We'll get 2 du equals dx over square root of x. And it's okay to bring a constant with du. That's going to be okay. So what happens is we take our integral, I'm going to rewrite it just a little bit so we have our dx over square root x. Well, this will become the integral of 1 over u squared times 2 du. And because this is a constant, it'll pass through. So you get 2 times du over u squared. The antiderivative for this, we're going to get negative 2 over u plus c. Or negative 2, and then u was originally 1 plus square root x plus c. And that's going to be our answer. Questions about that? So let's take a look at another one. Some tricky ones here.
Hi, sir, can you hear me?
Yes, I can.
I was going to ask you, where did the -2 come from? I know where 2 came in, but how did it get negative?
So what it is, we had an integral of du over u squared. So whenever you're going to integrate a variable, say like x to the n dx, your answer is going to be n plus 1 over n plus 1, exponent n plus 1, and then a denominator n plus 1. Now in this case, what we're actually integrating is u to the -2 du. They're the same thing. So that means we're going to get u to the -2 plus 1 over -2 plus 1, or u to the -1 over -1, or -1 over u plus c.
That makes sense. Thank you.
No problem. Yeah, any questions about these antiderivatives, just let me know. Now, again, these can get a little, they can get some interesting, how does one say it? There's some interesting tricks you might have to use with some of these. So let me show you an interesting trick. Yeah, sometimes these u substitutions take a little bit of guessing and just outright creativity. Now, this one's kind of hard because one of the things you look for when you do a u substitution, if we say this is u, then we want to make sure du dx is somewhere out here. And if we look for this, the derivative of this would be 2, but we have an x up here. So this doesn't look like it's going to work. But check this out. We're going to do it anyway. We're going to say let u be 2x minus 1. And then du dx equals 2. So du equals 2dx. And we're just going to send the constant with the du. That's okay. DUs can show up with a constant. But to be honest, this doesn't look promising. We would hope we had an x dx, but we don't. So what's going to happen? We'll replace the dx with 1/2 du. We're going to replace 2x minus 1 with u, but we're still going to have an x here. And for this integral to work, we need everything to be the same variable. So what can we do? Well, remember, u equals 2x minus 1. I'm just going to make a note here. What about that extra x? And that's what we're talking about. So this is what we can do. We can take this u substitution that we've made and solve for x. And when we do that, we'll get u minus 1 equals 2x. Divide by 2, we'll get 1/2 u minus 1/2 is equal to x. So in this type of scenario, we have to make 3 substitutions. We have to substitute for the u, substitute to get rid of dx, and then substitute to get rid of x. And so what this is going to give us so there's x. Here's dx. That becomes 1/2 du. And then, I have to make my integral sign a little bigger. Be taking the cube root of u squared. So let's see, we could multiply the 1/2 through. We'll get 1/4 u minus 1/4. Oh, I'm sorry, plus. It's a plus. I'm sorry. Wait, was it plus or minus? Let me double check. It was plus. I'm sorry, it's plus. Let me double check my notes. Yeah, it's going to be plus. So just to make a note, just in case if I wrote something not correct there, for x, it's 1/2 u plus 1/2. I want to just check your notes. It's 1/2 u plus 1/2. I might have accidentally written that incorrectly. But for your x, we're going to substitute this. And the cube root of u, another way of writing that is u to the 2/3. And we have du. We could factor out a 1/4 here on top. We can pull that 1/4 out. And then dividing everything by u to the 2/3. The integral of u to the minus 1/3 plus u to the minus 2/3. So any questions so far? All right. So now we do our integral, and same thing. We add 1 to each of these exponents, and we divide by the exponent plus 1, divide by the exponent plus 1. what we end up getting let me double check that real quick. It's a little suspect. Should be 2/3. Then we multiply through by 4. This will be 3/8 u to the 2/3 plus 3/4 u to the 1/3 Let's check something real quick. Okay. Pardon me for just a moment. The reason I'm dithering a bit here is that my notes say something else, but the calculation should be, I just want to check my solution here real quick. Oh, I see what it is. I apologize. Let me, oh, I see what it is. I'm sorry. I got a minus sign in the wrong place. Let me back up. There's a minus sign in the wrong place in my notes. Here, I don't want to give you the wrong answer. Yeah, something there didn't look right. So we have this, but this will become 1/4 u to the positive 1/3. That's what we want. Plus u to the negative 2/3 plus c. There we go. Sorry about that. I had a minus sign there in my notes. Let me cross that out. There we go. So let's start with this with a minus sign removed. And we're going to integrate this. We don't have our plus c just yet. And so when we integrate that, we'll have 1/4, here we go, 3/4 u to the 4/3 plus 3/1 u to the 1/3 plus c. Let me give you about 10 seconds, 10 or 15 seconds to make any corrections to your notes. And then what we'll do, we'll multiply through by that 1/4. And now we're going to replace u. Now u, if you recall, is 2x minus 1. So at the very end, we get 2x minus 1 to the 4/3 plus 3/4 2x minus 1 to the 1/3 plus c. And that's going to be our answer. So questions about that? So the last one really to show you for section 5.5, and then we'll go into 5.6, and it's really the same thing. We're going to continue on. We're just going to update it for definite integrals where we have bounds. Let's say we have something like this. So the integral of the sine of 2 theta e to the sine squared of theta d theta. And this is a sine square. It's not a sine 2 theta, but a sine square. Well, one thing we can do, we could make the following note. We're going to use some trig substitution here. The sine of 2 theta is 2 sine theta cosine theta. So that's going to give us this integral. Now I'm going to admit, this is looking ahead. One of the things with these types of problems, you're going to find yourself looking ahead saying, well, what changes can I make that are going to help this in the future? And what I'm eyeing is this. And this is why. If you let u be sine squared theta, then du d theta, we're going to use our chain rule. So we get 2 sine theta. That's our first part of the derivative. And then we do the second part, the inner function, derivative of sine is cosine. Or 2 sine theta cosine theta. So what we've got, this here is really this. And this is what we get when we take the derivative of u. So what we end up getting for du will be 2 sine theta cosine theta d theta. There's our u, and there's our du. So going back to that original integral, the integral of sine 2 theta e sine squared theta d theta. Well, we can rewrite this as the integral of e sine squared theta, and sine of 2 theta, that's 2 sine theta cosine theta d theta. And here's the good news. There's du, and then here is u. So what looks like a pretty difficult integral becomes the integral of e to the u du, which is so much easier. And the antiderivative of e to the u, well, you take the derivative of e to the u, you get e to the u, it's just itself. You get e to the u plus c or the solution is e sine squared theta plus c. So any questions about that? So now we're going to look at definite integrals. So now we're going to do the same thing except now our answer, which was capital F of g of x, it was f of u, but then u is always let to be g of x. But now we're going to evaluate from x equals a to x equals b. And this is just a way of writing evaluate. You'll see different versions. I think the text uses this. You'll see people write this differently. So in this case, what we can do, this becomes f g of b minus f g of a. And now we're going to work a little bit backwards. Recall that u is g of x. When we do a u substitution, we let u be g of x. So we can rewrite this as f of u, where u is g of a and g of b. And so where does this come from? Well, this comes from integrating little f of u. And we'll just give it bounds of g of a, g of b. So I'll be honest, the way I learned my integration is I just got everything in terms of x and evaluated bounds at x. You can do that also. That's perfectly fine in this case as well. But this is another way that you see this a lot. It's incredibly common. So I just want to make sure we spend some time going over this format because you'll run into it a lot. But when I learned this, they had us go all the way, bring it all the way out of u into x and evaluate the bounds at x. But that's probably a longer way of doing it. So in summary, if g prime of x is continuous on AB and F is continuous on the range of g of x. Because remember, g of x is going inside of f. So f is going to take the outputs of g of x, or the range. And let u equal g of x. And we're just going to summarize what we just did. The integral from a to b f of g of x g prime of x dx equals the integral from g of a to g of b f of u du. Questions about that? So, for example, the integral 0 to the square root 7 of t squared plus 1 the 1/3 dt. So we're going to let u, which is going to be our g of t this time, because we've got t as our independent variable. Let's let it be t squared plus 1. And again, the thinking is this. If we take the derivative of t squared plus 1, we're going to get 2t. So we're going to get a t left over as our g prime. Well, there's a t. So that t and the dt, they'll exit together. So du dt is going to be 2t. And so we could go with 1/2 du. Again, you can carry a constant with du. That's okay. Is t dt. And sure enough, there's t and dt. They're going to exit together. Go on vacation or something. So those are going to be our changes. Now, we can now come up, though, with the upper bounds. We could do this. So for our lower bound, u of 0, this will be 0 squared plus 1, or just 1. And then for u, square root 7, it'll be square root 7 squared plus 1, or 7 plus 1, or 8. And so that's how we can come up with the upper bounds in terms of u. So we're going to come up with an answer without having to go back to t. So this means our integral from 0 square root 7 of t squared plus 1 to the 1/3 dt. And there should have been a 1/3 up there. If I forgot to put it in earlier, I apologize. I have a 1/3 up here. Well, this will become the integral from 1 to 8. T dt is going to be replaced with 1/2 du, and this is going to be u to the 1/3. So the 1/2 pops out. It's a constant, so it'll work its way out. U to the 1/3 du. And again, this is going to be 3/4 u to the 4/3 times 1/2. And we're going to evaluate this from u equals 1 to u equals 8. Or 3/8. And then we're going to have 8 to the 4/3 minus, oh, here, I'll keep it, I'll stay in step. So you get 3/8. And then, yeah, I'm not going to skip any steps here. We'll go through all of them. U equals 1 to u equals 8. So we get 3/8, 8 to the 4/3 minus 3/8, 1 to the 4/3. So 8 to the 4/3, we have 3/8, comes out to 2 to the 4th minus 3/8 times 1. Or 3/8 times 16 minus 3/8 times 1. Or let's see, 48/8 minus 3/8. Double check this. 45/8. Something seems a little fishy on my arithmetic. Let me double check. Let's make sure. Let me double check that. Oh, no, that's correct. 45/8. So any questions about that? So the last thing to mention in this section, and this is something that you can use this in your computations. If you're doing any computer programming, there's some tricks here that could be really helpful. But working with symmetric functions. So we're going to talk about functions with different symmetries. And the two that we work with here is even, which means we're symmetric about the y-axis. So what that means algebraically, we take f of x and we put in negative x. When we simplify things down, we're just going to get f of x back. So what that means let's say we have something like this. We're going to have a function that's going to look the same on either side of the y-axis. So let's say we have negative a and a. So there's a trick we can use with this. And the trick's going to be this. The integral from negative a to a of f of x dx. So we're going to integrate here. So we're going to get this area plus this area. But these two areas, they're going to be exactly the same. So that means we can just take a shortcut and only integrate f of x from 0 to a and just multiply by 2. Questions about that? So just to give an example, it's kind of a simple example. Well, relatively simple. I don't want to call these simple necessarily. Let's let f of x be x squared. And sure enough, if we put in negative x, we're going to get x squared, which is our f of x to begin with. So this tells us we have symmetry across the y-axis. So let's say we're going to integrate this from negative 2 to 2. Well, instead what we can do is we can integrate from 0 to 2 and just multiply by 2. And if for some reason, like if you were working on a computer and you had to do numerical integration, you have to integrate a function, like, for lack of a better term, by hand, or if in your computer program you weren't using like a pre-built integration function. This would be a way of saving on iterations. You wouldn't have to use, and if you get into programming a little bit, a for loop is going to be quite as big. So this is where that can help. And so we do our integral. We'll get 2 times x cubed over 3 from 0 to 2. And that's going to come out to 16 over 3. Questions about that? All right. So another thing is odd. Another form of symmetry is odd. And this is symmetric about the origin. Now, algebraically, what this means, if we put negative x into f, simplifying, we get the negative sign passing through. So an example of what this typically looks like would be, say, something like this. So here's the key thing for an odd function. This has come up a little bit, but when you integrate below the x-axis, you're going to get a negative area. And when you're integrating above the x-axis, you have a positive area. So what happens if you integrate from here to here? Well, these two areas are going to be the same size, but with different signs. So what we're going to get is this, is the integral from negative a to a of f of x dx for an odd function. Those areas are going to cancel out, and you're going to get 0. So any questions about that? Excuse me. So for example, let's let f of x be x cubed. Well, sure enough, if you put in negative x, you're going to get negative x cubed. And that comes out to negative x cubed, or negative f of x. So that means we have an odd function. And just to show what happens, if we actually go through with the integration, this is just going to equal 0, according to what we've seen. But let's say we're not completely convinced. Let's just double check. Well, this will be 1/4, 1 to the 4th, minus 1/4, negative 1 to the 4th. And so that's going to be 1/4 minus 1/4, or 0. So it checks out. Questions about that? All right. So another thing that's going to come up is the area between lines. Or I should say between curves. You know, a little more general. And the way we handle this, it's the same as before. We're going to approximate these areas using rectangles. Pardon some artistic license. This is going to be an area A sub k. Here's f of ck. Now down here, squeeze that in. That's going to be g of ck. Point there. Here's f of ck. And then the width of this rectangle, let's call it, I'll label it off to the side. Delta xk. So the way we're going to set this up, first, any questions so far about what the graph is trying to show? Well, in this case, the main idea is we're still going to compute the area of a rectangle as a delta xk times the height of the rectangle, except this time the height of the rectangle will be fck minus gck. So a sub k will be f of ck minus gck delta xk. So the area is approximately now in the book, I think they put deltas here, like a little triangle, but they're going to refer to the same thing. We're going to sum these little areas. And then we're going to take a limit. The actual area will be the limit. And let's say we still have our partition somewhere in here at work, where our delta xk's are going to get smaller. The number of rectangles are going to increase. And so to find the area between two curves, it's going to be A to B f of x minus g of x dx. So questions about that? All right. So for example, let's find the area between y equals 2x squared and y equals x to the 4 minus 2x squared. Now, for something like this, it does help to graph, or at least have a sense of which function is above the other function. So I'm going to definitely recommend for this, graphing helps. That can be a huge help. Another thing you want to look for is where the functions intersect. Where do these functions intersect? So graphing, definitely recommend. It gives you a good sense of which function is going to be the f of x, which function is going to be the g of x. And then also, where do these functions intersect? Because this is going to give you your bounds of integration. Excuse me. So let's do that. Let's graph these two functions. Let's get a sense of what we're actually doing. All we know that we have two functions. There's some kind of area between them. Let's make sense of this. So the first function is y equals 2x squared. Again, pardon any artistic license on my part. Well, there'll probably be plenty of artistic license. Now, if we are to graph these, if we take a look at -2 and 2, when we graph these, we're going to find that it's these is where we get our points of intersection. And so what typically happens here is it does something roughly like this. Now, this is the other function, x squared minus, I'm sorry, x to the 4th minus 2x squared. Does something sort of like this. It's going to come through here. Let me make this a little more vertical. Does something roughly like that. And so what this tells us is that the area between these two curves is going to be this. So that's the area between the curves. Now, where these intersect, and the reason I picked out these two values of x is that's where you get the intersection. 2 and 8. And then we have -2 and 8. So when we graph these functions, this is what we're going to get, and this is what we're going to find out. The top function, the f of x, well, that's going to be the 2x squared. The bottom function, or the g of x, that's going to be x to the 4th minus 2x squared. And then the lower bound, we're going to start integrating, is -2. And the upper bound, where we stop integrating, that's going to be +2. So graphing these just to kind of see what they're doing, that's going to be a huge help for these kinds of problems. I mean, there's other techniques you could use too, but graphing is a real simple way of doing it. All right. So now we've got our pieces. Let's do the integration. So we're going to integrate from a to b, f of x minus g of x dx, or the integral from -2 to 2 of 2x squared minus x to the 4th minus 2x squared this will simplify to -2 to 2, and we'll get 4x squared minus x to the 4th dx. If we integrate that, we'll get 4/3 x cubed minus, let's see, 1/5 x to the 5th from -2 to 2. And there's some simplifying you have to do with the arithmetic, but the number you're going to get in the end is 128 over 15. Questions about that? All right. If I'm erasing too fast, let me know. If you want me to write something again, I can do that too. So the last thing in this chapter, in this section, is integration with respect to the y-axis. Or let me just say with respect to y. Don't get too carried away just yet. So this is a kind of integration that can make life sometimes a lot easier. There are reasons when you don't necessarily want to integrate with respect to the x-axis or with respect to x along the x-axis. You might want to go along the y-axis. And one of the reasons this comes up, and I'll bring this up in the example also. If you take a look at this area that we're going to try to integrate, you actually end up having to do some pretty complicated things here. So as you integrate from, say, here to capture this area, you're going to need a formula for the top part. Now, this isn't a function. These aren't functions. These are relations. They fail the vertical line test. So these are some kinds of what we call relations, which is a very, very generic version of a function where it's okay to fail the vertical line test. Very, very loose definition. And compared to functions. So what you would do is you would need to get a definition for the top part, because we're working with functions, what we're used to, a formula for the bottom part, and then you would use our formula for finding the area between two functions, this function minus this function, and then you'd have to stop, and then when you get to here, you have to divide this up into a top part and a bottom part, and integrate the top part minus the bottom part. And then these two areas, you'll have to add up at the end. I'll be honest, this could be a real nuisance. So there's a better way of looking at this. Let's try to look for, and I'm going to use a cursive F. If we can express these in terms of functions of y, here's a cursive G. If we could solve for x as a function of y, where x now will be the dependent variable, and y will be the independent variable. So this is the area we're looking for. This is the, relabel this as the y-axis. Then we can compute the area like this. The area will be the integral. So these intersect at y equals c and at y equals d. So instead of having to do two complicated integrals where we have to add them up, we can just do one integral in terms of y. And that's going to make our lives much, much easier. Questions about that? So we're going to do an example on this for sure. All right. Situation. Let's say we there it is. Sorry about that. I think the camera here is having some fits. So let's say we have this situation. Let's say we have this. And these intersect at 1, 1. And this is going to be 2. And this here is going to be x plus y is equal to 2. And we want to find this area. Now, again, we're kind of stuck in that 2 integral thing. One thing we could do is we could integrate from 0 to 1 of x squared dx to get this area. And then we'll add to that the integral from 1 to 2 of, and if we solve for y, we'll get 2 minus x dx. And that'll give us that area. So we could do that. But there's another way we could think about this. Instead of doing it like that, we can do it like this. Is it okay? So I'm just gonna give you another 10 seconds or so if anyone needs to write anything down. So instead of having to do 2 integrals that we're going to add up, instead what we're going to do we're going to do this as 1 integral. And this is going to be x equals 2 minus y. And then for this one, which was y equals x squared. Now this was, let me remind what this was. This was x plus y equals 2, and it's going to become this function. We're going to solve for x. Same thing here. Here we're going to solve for x. We're going to get x is the square root of y. And this is for x greater than or equal to 0. And so what we can do, if we take a look at this, this is going to be our capital F of x, or cursive f of x, f of y, pardon me. So this is going to be our f of y, and this is going to be our g of y. So f of y is going to be 2 minus y. G of y is going to be the square root of y. And again, the intersection point hasn't changed. So here's f of y, quote unquote, on top. Here's g of y below f of y, so to speak. And then here, again, we have 1. So where c is going to be 0, and our d is going to be 1. And here I'll give g of y the coordinating color. So questions about that? So what this is going to tell us then, instead of doing 2 integrals that we have to add up, and sometimes those 2 integrals could be very complicated, what we're going to do is get the same area by integrating with respect to y. And this is going to be evaluated from y equals 0 to 1. And if you were to hammer that out, you'll get 5, 6. So depending on the kind of integration you're going to encounter, it might be simpler to integrate things with respect to y instead of x. And that's what this gives you an option to do. So any questions about that? All right. So it just dawned on me. Maybe it's just my memory sort of fading a bit, but I don't know if we did an example for something like this with the negative areas. So since we do have 10 minutes left, we're a little early. And I'll talk about the exam as well. I think we did get into this when we talked about the difference between displacement and distance traveled. But I'd like to at least do an example with this. Let's say we're going to look at the integral from, let's see, negative pi over 2 to pi over 2 sine of x dx. So if we think about this, if we draw our sine, in fact, let me switch it up a bit. Let's make it a little simpler. Let's go negative pi to pi. Now, usually something like this is going to be an odd function. And usually what that means is that if we integrate symmetrically, in other words, from negative pi to pi or from negative 2 pi to 2 pi, you're going to get a total area of 0. So our sine function does something like this. Let me drop this down. So when we're thinking about the area from negative pi to pi, and again, I apologize, I've got artistic license going on here. But we have these two areas. The one below the x-axis is negative. And above the x-axis is positive. So if we do the integral of this function, what it means is that if we integrate from here to here, we're going to get 0. And this is the same thing we saw with the symmetric functions. So the integral from negative pi to pi sine x dx is going to be negative cosine of x from negative pi to pi. It's negative cosine because if you take the derivative of cosine, you'll get negative sine. We've got a positive sign. So negative sine times a negative gives you that positive sign. Negative negative 1 minus negative negative 1, a bunch of negatives. 1 minus, this becomes positive, 1 minus 1, and sure enough, we get 0. Excuse me. So if you do the integral, you're going to get 0. And so what'll happen if we want, say, like the total area of the function between itself and the x-axis, excuse me, for total area, I'm going to find where f of x crosses the x-axis. This is one way you can do it. Another way you can do it is you can do this, and you can use these crossings. You can take the, we're going to need these crossings actually. We're going to break this up. I'm going to say it's equal. We're going to break it up to find the total area from negative pi to 0, because this function crosses the x-axis at 0. Excuse me. It's allergy season, so I'm getting kind of mute. Well, anyway, it's allergy season. and add the absolute value. In this case, you won't need to take the absolute value for the second integral, but yeah, you could if you wanted to. But you would break it up like this because f of x crosses x-axis at x equals 0. So now we're going to do these two integrals. So you'll still get negative cosine of x, negative pi to 0, plus the absolute value of negative cosine of x from 0 to pi. Easy to confuse these absolute value bars and your integral bar. So negative cosine of 0 minus negative cosine negative pi plus negative cosine of pi minus negative cosine of 0 . And so we go through and evaluate. So this will be negative 1 minus cosine of negative pi is, let's see, cosine negative pi is also going to be negative 1. Makes it a positive 1 minus 1 plus cosine of pi is negative 1 times negative is 1 minus cosine of 0 is 1. That makes it negative 1, so that's a positive 1. And so we end up getting is the absolute value of negative 2 plus 2 . We get 2 plus 2 is equal to 4. So the thing is, it's the strategic uses of the absolute values. You put the absolute value on the integral for intervals between where the function crosses the x-axis. And that's the idea. So any questions about that?
Yes. When would you use the absolute values instead of just getting 0?
If the first thought that comes to mind is something geometric, so if you wanted to find the area between the curve and the x-axis, regardless if the area is positive or negative. So if you were looking for something, say like this, you have a function that's doing something like this, you wanted to find the total area here. That's one way you could do it. Now, the other thing they mention in the text is displacement, where if you take a velocity curve, and it works like this. Distance traveled is velocity times time. So if you have a velocity curve, so you have, say, like here's time, here's velocity. And if your velocity curve does something like this. So here you have a positive velocity. A negative velocity might mean you're traveling backwards. And then let's say you have something like this. So the idea is going to be this. The integral of the velocity function with respect to time, this is going to give you something called displacement. Abbreviate displacement. But this is how this area here is how far you've traveled away from where you started. This is also additional distance. So this is d. So we could say this area 1 and this area 2. Area, you can think it again as roughly velocity times time. So this area is going to be roughly a velocity times time. This is going to tell you, the area will tell you how far you've traveled away from where you started. This is additional distance that you've traveled away from where you started. But here the velocity, that means you're driving back to the starting point. So this to take away from the distance you are away from your starting point. So you could have driven 10 miles, driven 5, tracked 7 miles. So if you've gone 10, you've gone 5, that's 15, but you backtrack, say like, again, we'll just put the numbers in, 10, A2 is 5, A3 is, say it's 8, or 7, I think we said it was 7. In this, it'll be 10 minus 7 plus 5, or 8. So that's displacement. When you get this negative area, what that actually means, it's taking away from your distance traveled. But let's talk about something else. If we take the absolute values, so displacement's what we get when we just integrate. Total distance traveled is what we're going to get when we take the absolute values. And that's going to come out to 10 plus 7 plus 5, or 22. So if you're thinking about how far away you can get from your starting point, like let's say you're doing a model rocket launch, a really fancy model rocket launch. So maybe you're going 10 miles and then you backtrack 7, like we don't need to go that far. And like, oh no, we need to go farther. You go 5 more. And so you're finally 8 miles away. That should give you a good view of where the rocket's going to land. Now for your tires, the wear and tear on your tires don't care if you're driving away from a point or driving back to it. You're putting wear and tear on your tires. Your tire is going to be interested in this, distance traveled, and that's going to be the difference between the two. Does that help? I don't know if that makes sense or not. But that would be the reason you would use one over the other. If you're just interested in how far away you got from a starting point, you would just integrate this velocity curve over time. But as far as your tires are concerned, they're interested in wear and tear, regardless if you're heading out or coming back. And they're going to want to know what's the total distance traveled. In a way, you can kind of think about it, your odometer on your car, it works with this. It doesn't care at all if you're driving north, south, east, or west. It just wants the distance that you've traveled. Questions about that? All right. So that's it for chapter 5. So what I'm thinking of doing with the exam, we need 3 days of lectures left, and we've got 4 days remaining before finals week. So what I'm thinking of doing is doing the test. I'm going to try to get those solutions out today or tomorrow, but the test will be, I'm thinking either Monday or Wednesday. So I'm going to ask you, which would you prefer? You can study really hard on the weekend, and I'll take a look at the homework schedule, maybe make some adjustments. So I know we packed some homeworks in there. I'll take a look if there's anything I can adjust, but it will be multiple attempts, correct? I'll take a look. I'm thinking Wednesday. I'm leaning towards Wednesday. And so I'll take a look at the schedule. I'll make some adjustments, and if I think is a humane schedule, and I'll get you those solutions out as soon as possible. And other than that, let me know if you have any questions, and then we'll finish up. We'll do chapter 6. Chapter 6 is applications of integrals. We're going to be looking at calculating volumes, and we'll be looking at calculations of work and center of mass and things like that. And then that's it for the semester. So unless you have any questions, let me know. Other than that, have a wonderful afternoon.
Since I'll be gone next week, should I take the test after? Will I be able to do that?
I